Hi, welcome to this new lesson. We've seen in the previous lesson how to make an image classifier. This image classifier was able to take an image and tell us if it was either a vertical line or a horizontal line. There were a few drawbacks with that method. Most of all, we were just guessing the filter, and so to get some reliable results, it could take really long time and we were not sure we were going on the right direction. So we're going to see right now for the first time a neuron. The purpose of a neuron is to take an input, process the information, and gives us an output. So if the image is a vertical line in this case or a horizontal line, which is the same purpose that the image classifier had, with the only difference that the neuron has some way that it can learn from its mistakes. For the moment, we are just going to see an introduction how the neuron takes the input and gives us an output. We will see that visually, so I will draw that on the screen, and also we will see some example with Python. Let's start. Here we have the whiteboard. Now we're going to see the neuron, what it takes, what it does, and what it outputs. And then we're also going to do that operations manually. We'll start working with our vertical line. So this was the example of a vertical white line that we used before. That's our input. And as you know, the image must be pre-processed. We cannot just take the image and give the image to the neuron, but first we need pre-process the image by flattening the image. So here is the image flattened. And as you saw in the image classifier that we did before, we convert the white pixels to 1 and the black pixels to 0. So this is our image and it will look something like this. So this corresponds, black pixel is 0, white pixel is 1, black pixel 0, black pixel 0, white pixel 1, black 0, black 0, white 1, and black 0. This is what we call the input. Now, if you remember, in the image classifier, after we took the input, we multiplied the input with a filter. We are going to have something like that also on our neuron, but let's use now the proper terminology. So what we called before filter is what in neural network is called weights. And so we add now the weights. And as we did before, we're going to put some random weight from 0 to 1. So keep in mind, when we choose the weight, they have to be from 0 to 1. And to make them as neutral as possible, I will put 0.5 for each of them, 0.5. And the weight must be as many as are the inputs. So we have 9 pixels, so 9 numbers, so we need 9 weights. And I will put 0.5 for all of them. 0.5, 0.5, and then 0.5. You remember when we did the image classifier, we did the operation where we multiplying the input with the weights. And we do the same right now. So we're going to multiply everything. So this is the operation to multiply all of them one by one, of course. So 0 per 0.5 is equals to 0. 1 per 0.5, 0.5, then 0, 0, 0.5, and then 0, 0, 0.5, and then 0. The next step was to make the sum after the operation, after multiplying the input with the weights, make the sum of the result. So we do the same right now. And our sum will be equals to 0 plus 0.5, 0, 0, 0.5, 0, 0, 0.5, and 0. So of course 0 plus 0 is always 0, so we add 0.5 with 0.5 with 0.5, and we get a result of 1.5. Then for our output, so I will add the output. So output to tell us if the image was a vertical line or a horizontal line, we use a condition. So we can say if the sum is less than 0, then is vertical. If greater than 0, then it's horizontal. So horizontal. Now, making this sum, we started with a vertical line, we make the sum, and now the result is 1.5. 1.5 is greater than 0, and we get as a result horizontal, which is wrong. It's wrong. It means that the neuron doesn't have proper weights to give us a correct output. In the previous lesson, what we did in this case was just to discard everything and say, okay, the result is not correct, so let's try again. We would make random weights until we were able to get a result that was greater than 0 for the horizontal and less than 0 for the vertical. With a neuron, things work differently because the neuron has the capacity to be able to learn from its mistake. So that's the key of our neuron. We need to make some change with this condition. If you notice, for example, now we got a value of 1.5, which is wrong. So we are sure it's wrong. But even if we could get something like 7.5, and 7.5 is farther from 0 than 1.5. So 7.5 will be even more wrong than 1.5 is. So if we would get 7.5, we will be sure there will be higher mistake than 1.5. 1.5 is wrong, but it's not so far from 0. So that's the key of the neuron, where we need to make some change. So we cannot use anymore the condition if less than 0 and if greater than 0. Instead, we need to find a way so that we can understand how close or how far we are from a correct prediction. So let's do that. I'm going to cancel this condition, and instead we will put vertical and horizontal into a range from 0 to 1. So we can say that if the result is 0, then it will be vertical. And if the result is 1, then it will be horizontal. And between the weights operation and the output, we're going to add what is called activation function. And I can put that right here, activation function. which has the purpose of taking these numbers and make it as close as possible either to 0, either to 1. So if the result is less than 0, it will give us a result really close to 0. If the result is greater than 0, it will give us a result really close to 1. A really common activation function is the sigmoid function. So what we do, we take this value and we use this value with the sigmoid function. So it will be the sigmoid. Instead of this, it will be sigmoid of 1.5. And what is the sigmoid value of 1.5? Let's check that right on a graph. So I'm going to plot a graph right now. Here we have the sigmoid function. So we have a value of 1.5. So 1.5 is somewhere here. And now I'm going also to draw it on the screen so that it will be more clear. Here is the sigmoid, so all the values you can see here on the x, so we have from -8 now till 8. If a value is less than 0, so all this part right here, then it is going to give us a result between 0 to 0.5. If the value is greater than 0, so from 0, 8 and plus, of course it can go infinite. I've just got this on the graph from -8 to 8 not right now because of matter of space. If it is greater than 0, so it is going to give us a result between 0.5 and 1, and will be all this part. So now we got a result of 1.5, so 0, 1, 1.5 should be somewhere right here. And so let's go up and let's see what is the sigmoid value of this. So it's 0.8 approximately. So we have 0.8. Let's go back to our visual representation of the neuron. As a result, we get 0.8. Of course, it might be a bit different, 0.81 or something, or 0.79. I'm just going to approximate the numbers so that you can have an idea. We have 0.8 and our result is supposed to be vertical. So it should be closer than to 0, but it's not, so it's not correct. So as it's not correct, we can calculate what's the error. How do we calculate the error? So we say error, and we have here our final result, which is 0.8 minus the result that we were supposed to get, 0. So we get 0.8. So this is how far we are from the detection to get vertical. If it was, for example, 0.2, we will know that the error was much less than this one, and we will be much closer to our result. And these two values, which are at the moment are the same, but it's just a coincidence, they're going to be really useful later when we are going to train the neuron. For the moment, it's all for this visual explanation of the neuron. We will see how to train the neuron in the next lesson. Let's instead now move on with this, and let's go and write this neuron with Python. I'm going to start with this file where I have already the sigmoid function we are going to use this one. I'm not going into the explanation of the sigmoid. The only goal for the moment was to show you what was the goal of the sigmoid function. Let's now represent the same I did visually, but with the code. The first step was to take the inputs. So inputs. The inputs, we will take the image. So we load the image, cv2.imread. We take the image from images, and then vertical.png, and we need to load this image into grayscale format. Imread grayscale. And I forgot to import cv2. Of course, we need to import cv2. Then let's call this the preprocessing of the input. So first is input, then the input, we need image preprocessing, which are the same operations that we did before for the image classifier. So we need to divide the image, all the pixels divided by 255, and then we need to flatten the image. EMG is equals to, let's say EMG flattened equals to emg.flatten. Let's make sure that everything is correct, so we can print emg flattened, and we can run this, and this is exactly the same representation of the input numbers I did before visually on the board. Now we need to create the weights. So the second step, weights, and the weights, in that case I created them manually. Weights is equals to np.array, and then 0.5, 0.5, 0.5, then we have 9 of them. 0.5, I can copy them again. Now we have 8 and then 9. Then we multiply the weights with the input convolution, and then there will be also the sum to make the full convolution. It will be emg flatten multiplied with the weights, and then we have the sum, and we can print now convolution. So I run this one and we get the value of 1.5. And then through activation function, sigmoid of 1.5, so we can say that our result, and we print the result is equals of the sigmoid of 1.5, and so we can print the result, and we get 0.81 and such long value. Finally, the output. So based on this, we have 4 output. The output, we can say if the result is less than 0.5, then we can print its vertical, and if the result is greater than 0.5, then we can print its horizontal, and we can run this one. So of course now we get horizontal because our neuron is really dumb. It hasn't been trained, so it doesn't know what the image is yet. We know that now it says horizontal, but we also know that how wrong are we to be close to the vertical. So after this, we can at least, even if it's wrong, we can at least calculate the error. So fifth, we have the error, and error will be the value of vertical. So we say if vertical is supposed to be 0, in vertical 0 and horizontal 1, the error, which is equals to the result minus vertical. Vertical is 0. If it was horizontal, we would put -1. And of course, now we're just putting the number, but later we will see a better way to represent the vertical and horizontal so that we don't have to put manually the number each time. And we will use this error later on in the next lesson to train our neuron. So we can print error, and then error, and we can run this one, and we see the output, this one, the result, which at the moment corresponds with the error. This is all for the moment. See you in the next lesson.